Hello everyone and welcome to lesson number 20 of the FX Masters program. Um, I think it's time. It's time to start talking about fluids. So far we have 19 lessons. We've been talking about particles and everything related to them. I don't think we have finished talking about them, but I think it's a good opportunity to begin with fluids. This lesson, I'm gonna give you a bit of an introduction of how the fluid solver works and my experience and my tips as usual. And then on the next lesson we're going to do our first test with fluids. We're going to work on the ash that it's in the air, the ambient ash that you see in this shot and this sequence here, right? um, I think it's very important for you to see the real, in my opinion, what is the real power of the fluid solver, which is it goes beyond what you used to see, which is smoke and steam and explosions and dust. Um, in my opinion, yeah, that's fine. We're definitely gonna do a lot of examples about those things. But in my opinion, I think it's best to start with what I believe, or what I use it for the most part. Is it's an atmosphere as a force field for particles and pretty much anything else. Um, you will see that you will unleash like a huge amount of power now, and then your simulations will begin to look a lot better. You will have a lot of more, add more realism to whatever it is you do. I believe that once we start, you know, playing with fluids and testing them, I think it's a good opportunity for you to go back to the first few lessons and see where you can start applying these things. So, for example, we can improve the look of the penguins scene, for example. We can go ahead and add atmosphere to it. Doesn't have to be, it could be, but it doesn't have to be necessarily just a snowstorm, for example. It could be just an atmosphere. Um, the scene with the sea lions, for example, you can go back and add the particulate in the water. Remember that's what actually makes a proper underwater look. It's just the particulate and the lighting. So movies like Finding Nemo and all that, they wouldn't be successful if they didn't have that kind of particulate, right? So I think what we're going to learn today and on the next lesson, it can easily be done and used for that kind of stuff. You will find many applications for it. So let's start with that, and then let's go later to the normal, more regular explosions and things of that nature. So with that in mind, before we can jump into fluids, anyway, you should be watching, if you haven't, the Maya Dynamics Level 2 of the FX Power User program, which is the entire level. It's pretty much about fluids. So we're gonna have you have a lot more examples in there, and probably more in-depth explanations, right? But that doesn't mean that we shouldn't talk about them right now. And to me, the most important thing that you should understand with fluids and master is the concept of scale and understand how it works and why some people, the people that are not experienced enough, tend to sometimes misinterpret what the fluid solver is doing and then make statements like Maya is slow or Maya is shit or the fluid solver is old, or you will see that it's a complete mistake to think that way. Most artists, okay, most junior artists and people that are not experienced, they will tend to make some of the mistakes that I will point out today and probably ignore completely the sense of scale and why, okay, the simulations are failing for them and waste time just unnecessarily, right? So to me, the first thing we should discuss, I think, is the sense of scale, right? So for that, I found this morning when I recorded this lesson in Spanish that it was the best example was for me to bring a familiar character, which is this one, from the Doctor Strange lesson. You know him, right? I'm going to bring him up here, okay? And I'm also going to import going to import the zebra from the lessons, a few lessons back. So 2 characters that you have seen before. So I'm going to get rid of this, and I'm just going to stick to the zebra, which is right here, and the monk, which is right here. So first thing, you will receive a scene at work from a client, and they will just create their scene and their camera and their animation. They will just, that's fine, right? They just hand it over to you, and they'll ask you to do a fluid simulation. Any fluid simulation, doesn't matter. The first thing you need to do is just check the scale. So right now, for example, if I had no grid, if I have him, right? I don't know, ignore this part. So I'm actually going to put the zebra on his own layer. Okay, so let's assume that I have just this guy right here. And he has a floor and walls, and he's on a set, and he's being looked at through the animated camera or whatever. I have no idea about his scale relative to something else. So if he's just him on the scene, right? He could be the size of a pin, or the size of a person, or like a ginormous statue from a film. I don't know how big he is, because there's nothing else to compare it to, right? So everything in his world related to him, looked at through the camera, is proportionate to each other, right? But that doesn't really help me, okay, if I'm going to be working with fluids. With particles, we got away with not thinking too much about the scale. We talked about scale in terms of how fast or how slow the particles are moving, and the feeling that actually gives you, right? But in terms of fluids, scale, relative scale, is very important for us. So how can I tell, okay, if this guy is too big, too small, or if he's in the right size? My advice, okay, is to do this. You go to your effects menu, you go to your fluid solver, fluid tab that we're going to be working on, and you're going to create a 3D container. And there it is. You will see this. All right, that's fine. So if I'm going to make a fluid simulation for him, let's say that something simple, let's say that he's just, he could be on fire, for example, right? Or he's just, I don't know, smoking because of something. I don't care, right? My point is, if you're going to do a fluid simulation for him and you create this container, it looks like, for what I can see, right, for what you can see, it feels like this container is way too big for him, right? I will have to scale this container down and make it fit better. One of the things with fluids is that you cannot waste. With particles, you know, we have it's a bit more understanding and a bit more forgiving, I will say, particles, right? But with fluids, you have to be very, very careful with every single bit of space that you have. So wasting space, wasting this big volume that you have right here, it's unnecessary. It's going to make your life more uncomfortable, right? So what you should do is then just, okay, I'm going to have to scale this thing down. If you don't know, if it's the first time you're playing with fluids, you might grab this and jump here, right? Or grab your scaling tool. Don't do that ever, okay? Write it down on a little piece of paper, glue it around your computer. Don't do that. Don't scale fluids like this. No, don't do that. It's very, very bad for you. Fluids need to be scaled in a different way. I will show you now. By scaling fluids this way, you're just messing with the calculations, you're messing with the solver, and it's not going to work. So that's the first rule. Never scale a fluid with a scaling tool or in your channel box. Never. So what do we do? How do we scale this thing properly? Well, we need to select it, go to the attributes, and then here under the fluid shape, okay, on the first tab we have the container properties, and especially what you need, which is size. Okay, size in X, in Y, and in Z. Correct? Here is where you change the scale of this fluid. So now what happens? You will have to scale it, you have to go use smaller numbers than this. For example, you will have to use, let's say, for the height, let's say 5. Okay, you can see that the fluid scales and it's scaling correctly. You can move it, no problem, but you should never scale it using the scale tool. Rotation, I wouldn't advise to do that, but it's not as bad as scaling. So anyway, you grab your container, you scale it to 5, you're fine. And I don't know what else you're gonna do, but probably you will need to go below 10 on each axis here. Well, that's another advice I'm gonna give you. Don't do that, ever. This is how you judge if this model is too big or too small. At least in this case, too small. Why am I saying that it's too small? There's not such a rule. You're not gonna find that in documentation. Okay, this comes from years and years of experience, and I've been using fluids on a daily basis for quite some time. Okay, so I have discovered and come to certain conclusions based on my experience, right? So I determined that a fluid container or a scene file, in this case my character, is too small because I have to go below 10 on the size. If you have to do that, then it's too small. You should never go below 10. Never, ever, ever, ever go below 10. Why am I saying this? The fluid solver, okay, the fluid container is run by what is called a fluid solver. The fluid solver is a node, is a collection of algorithms and expressions and method, formulas, and okay, that is self-contained. Okay, they will do their own calculations in order to have the fluid simulation to work and run. Those calculations will run with decimal points and precision. If you have to go too small, below the default size of 10, then those calculations might not be as precise, and that might translate into unstable simulations and problems. This solver needs to have a proper scale in order to work correctly. So, first rule, well, it's not the first rule is not scale it. Let's say second rule, don't go below 10 on the size. If that's happening to you, then you're gonna have to grab your guy and scale him up. Yeah, that might be too big. But I think I should, let's say that that's fine. Let's just put him with a scale of 5. Okay. All right, so this guy now lives and sits inside the container. Yes, we may need more space, but at least I'm not going to have to go below 10 on each one of these axes. That's very, very important you remember that. A scene can be too big, and that's mostly the case, but also can be too small. So with fluids, you have to find a sweet spot in between those two. Don't go too far on the big size, scene they're too big, and don't go too far on scenes that are very small. Okay? If you have a camera, if you have animation, don't worry about it. You have to scale it all. You have to do it. What happens? If you're in a studio, okay, that is decent in the way they work, meaning that have decent experience with effects. Okay, they have someone with some sort of experience. Someone will bring this up, probably. They should. They should bring it up. A supervisor should bring it up when you're doing layout, when they're doing animation and modeling. They should point that out that whatever geometry and animation and cameras that they have are going to be involved in the fluid simulation. So the scale is going to be important for you. You don't want to receive something too little or something too big. So it should be their job. If not, my advice to you is don't worry about it. Don't say anything. Just scale your scene. Grab everything in your scene, camera, everything, and group it and scale it up or down depending on what you need in order for it to fit in your container or in a decent size container. I'm not saying you have to always do this and scale it very little. No. But you have to make it fit. In this class, I will show you the two situations, right? So that's the first situation where a fluid container or a scene file, or geometry is too small. And this is how you determine that. Okay, what happens in the opposite scenario? So I'm going to grab this and I'm going to hide it and I'm going to bring my zebra, which is right here. Yeah. Okay, I received the zebra and I create a default container and it's this size. Okay, so what does it mean? Well, it means that I have to go in here and scale this up. Okay, there we go. And let's say that this little guy Okay, it's going to be moving along, so I think I need more space in the z-axis. Let's say for something like that, right? Where this animal is going to be moving a little, this walking or something. Something's going to happen and it needs a little, this little bit of space. Okay, this is a situation which is the opposite side. Opposite side, I'm sorry. You have a way too big of geometry. Why do I say this? Okay, so I said when it's too small, it's a problem because the calculations are not as precise and you might have issues with that. When it's too big, it's going to start becoming a problem because your computer is going to run out of resources. Before I explain this a little bit better, let me just show you something. Right now, you have this, okay, grid, let's say at the bottom. Okay, you have all these squares right next to each other, right? That's a representation of what is called a voxel, and I'm going to show you that in a minute. What this is telling you, and this is here for a reason, is here to show you how big each one of the subdivisions inside this volume it is. Each one of these spaces, okay, is what Maya is using to calculate all the forces and everything related to the fluid container. It's splitting that into all these little cubes. And the information from one cube is going to affect the one next to each other. And you hear me say cube, 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 but you all you see is a square, right? But it's not really a square. This is just a representation. If I grab my container and I go in here in the fluid shape and I go to display, open this up, here on the boundary display it says bottom. Normally what's happening is this. Okay, full. And look what's happening. They're actually cubes, as I said before. That's why I refer to them as cubes, because I already know what's happening in here. So this volume is subdivided into cubes. Each cube is called a voxel. So a pixel, right, is a two-dimensional thing. A voxel is a three-dimensional thing, so it's just a cube. A little small volume that is one small part of one big area. Okay, one big volume right here. So each cube is what Maya is calculating separately, and the information just moves along from one to the other, and that's what the simulation will run through. Now what happens? The bigger these voxels are, okay, the faster your simulation is going to be. Yes, but it's also going to be less detailed, right? It's just like having a pixelated image. Okay, if you have big pixels, you have less pixels, it's faster to process, but it doesn't look as sharp as something with higher resolution. Okay, same idea here. Exactly the same idea. So some people, and most of you might wonder, well, but okay, so what is the appropriate number of voxels to have a simulation that it will look, pretty good? And no one will ever be able to tell you exactly how many voxels, because there's no such an answer. Because at the end of the day, it's not really the amount of voxels that matters. That's the tricky part, and that's the part that's so surprising to me, because not Autodesk and not any other courses or those so-called universities that teach these things have been able to determine, and I don't see why, because I came to that conclusion a long time ago. And to me, the easiest way for me to teach you to predict, in a way, how it's going to look, and most importantly, if your computer is going to be able to handle it, okay? The way that I have to anticipate those things, in a way, okay, it's not a rule, but it's quite effective, is to think of these things, of the fluid container, in terms of relationships or ratios. Okay, a ratio of what? A ratio of the size of the volume, okay, against the number of subdivisions or voxels that you have in each one. Yeah? Thinking of it in terms of ratios is easier, because you may have a tiny little container that we saw with the monk, that it may need less number of voxels than this big one with the zebra, right? So number of voxels is impossible for you to judge if it's going to be good or not, because what it could be high resolution for the monk, brought up to this big scale for the zebra, is going to be low resolution, right? So for me to tell you a number, what, 1 million voxels is enough, or 2 or 3 or 20 million, we don't know. We will never know, because it depends on the size of the container, right? So it's very, very important that you start to think of it in these terms. And when you present this work to me on the support group, I would appreciate if you when you mention your simulations, you will, and that's something for you to practice when you go to dailies and things like that, right? And even in my professional work, okay, I'm not going to say that my coworkers did this, never. I came up with this way of explaining these things when I was recording the first, or teaching the first time Maya Dynamics Level 2. So I was trying to find a way, how can I just explain my students and have them see what I see in my mind, right? So I think of it in those terms. You're never going to hear that in dailies, but I think it's useful for you to start getting, into the habit of talking about fluid containers in those terms. That way your teammates, okay, in this course, and myself, I'll have a better idea, okay, of where you are in the process. So when you present your work in the community, please just say, okay, this is my simulation, I did this and this and that, and this is and give me the ratio, right, that you're doing. I'll show you how to do that. So basically you have this, okay, this volume that is subdivided into these voxels, yeah? And in here, you get the information that you need in order to determine the ratio. Right now, I'm going to open my calculator and do this for the first few times until you get really, comfortable with fluids. Right? Keep your calculator around and do what I'm going to do. My ratio is if I divide the base resolution number, which is right here, by one of this size, usually the biggest one. So my base resolution is 10, okay? Or you can do it here in the resolution as well. You can divide, okay, the biggest resolution by the biggest size, right? So I'm going to divide 10 divided by 1,000. And then you get a ratio of 0.01. 0.01. That's your ratio of voxels against the size of your container. Okay, so here I can tell you, a ratio of 0.01 is absolute crap. Useless, not useful, useless. It's not a ratio that is in any way close to what you're going to be doing for rendering. It's not precise at all, okay? It's just nothing. It's just very simple. Any cell phone can calculate this thing. You'll be fine with that. But at least it tells you an idea of a ratio, right? Now I can tell you another thing. A ratio, for example, for a simulation for film, okay? Something is going to be on a big screen, on a movie screen or on a HD TV or a 4K TV, okay? A ratio for that is going to have to be 10 to 1 at least. And once again, I should point out, this is not a rule. This is based on my experience. Probably once you start practicing, you might have a different conclusion, but given that I've done this for so long, then it kind of works to me that way. So a ratio of 10 to 1, anything over 10, okay, is a good ratio for film. Sometimes you may need more, sometimes you may need 10. But I think a decent resolution would be 10. So what happens here? If that's the case, and I'm working right at the moment at 0.01, I'm way too far from my goal. So let's figure out how can we get the goal and how do we know if my computer is going to be able to handle this, right? So in here you have something called the base resolution. The base resolution is a number, okay, of voxels that is going to be applied to the biggest axis of the three. Okay, so I get my X, Y, and Z. My longest axis is the Z axis, as you have here, correct? So my base resolution, as you can see, is assigned automatically to this side. And thanks to this checkbox right here, which is called the keep voxel square, if it's not checked, you should check it always. Yeah, very important for that. Maya should be working with cubes for voxels. You don't want Maya to be working with any other shape, meaning that unproportionate shapes, right? So if you check this on, Maya will do automatically what we used to do by hand back in the day. Right? We need to figure out these values in here. And yeah, when you're using round numbers, it's easy, but when you're using, 1,293, it could be tricky to figure out. It takes time to figure out the other two axes. So It's easier if Maya put this on and Maya will do the calculation for you. So basically what happens is you got your 10, which is assigned to the longest axis, and then each one of them happen to be an easy number. It should be half of this, so you get half of the voxels on each. Okay. Again, how many voxels do we have? Well, we have, to know the voxels, you need to multiply these three numbers of the resolution, 5, 5, and 10. So you go 5 times 5 times 10, and you get 250. 250 voxels. That's what you have on this container with the zebra. Yeah? Like I said, 250 voxels is nothing. But look what I'm saying. 250 voxels for the monk is going to be a lot more of a ratio of what it is with the zebra. Right? So the ratio is what's mattered to me. 0.01, we calculated that already. But just so you know, you have 250 voxels. If you want to verify this, you can go to like a top view kind of thing. Let me just, okay, top view. You grab your container, and you can check. You have 5 in X, so this is my X axis, right? It runs like that. So you get 1, 2, 3, 4, and 5, no problem. You get 10 on my Z axis, which runs along this way. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And as you may imagine, in Y, we also have 5. So 1, 2, 3, 4, and 5. So that's correct, as you can see. So in here, you have 250 voxels for your simulation. And like I said before, any cell phone can do this. Not a problem. Okay, so now going back to the topic of the ratio and the number of voxels. I'm saying if I were to render this simulation for film, I need at least a 10 to 1. So let's figure this out here. If it's 10 to 1, meaning that I need 10 times more, okay, voxels on my resolution than the size of a particular axis, right? So in this case, if I need 10 times more, I have 1,000 here, okay? Meaning that if I need 10 times more, I'm going to have a 10,000 up here. I'm not going to put the number here because I know that my computer might crash. This is how delicate it is. So we're going to do this using our imagination. Okay, so if this is 1,000, I need here 10,000. So I'm going to say 10,000, correct? If I have 500 here, I'm going to need 5,000 in here to be 10 to 1. So multiply it by 5,000. And the same story on this axis. So it's equal to this, multiply by 5,000 again, and then you get this ginormous number, which it is what? 6 numbers to a million, okay? A billion to what? 250 billion particles? I'm sorry, particles, not voxels. You will have to call Captain Kirk and Darth Vader to come in and help you calculate that on the freaking Enterprise and the Death Star, because there's no computer on this planet that probably can do this thing. Okay, this number is impossible to calculate for a computer as a fluid simulation, I'm trying to say. It's impossible. For me to get a 10 to 1 ratio, I'm going to have to put in my base resolution 10,000. In Maya, just by putting that and trying to draw that is going to fail. There's no computer that's going to handle this. That's when you start hearing people, okay? They have no experience complaining about this. I'm not saying they go that far to 250 billion voxels, but I know that they make mistakes because I've seen it. They don't care about the scale. They think they're just making a container big enough and just bumping up this number. It's going to make their day. It's going to save their simulation. And that's not the case. Then they start complaining that Maya's shit, that this and that, that the Pyro solver is better, or this, or the Cinema 4D, or their grandmother can do it better. I don't care. It's not true. It's not true. You have to work smart. I believe that by now, that concept is quite clear in this course, that you need to work smart. Working smarter and efficiently is better than having a strong computer. I promise you that. I promise you this. Working smart and understanding this is the key. So that's why I put so much time and so much effort into making these concepts extremely clear for you. So 250 billion voxels is impossible. So a ratio of 10 to 1 in my computer or in any other computer that you will ever touch is not going to happen. Okay, so what do I do? Do I compromise the quality of my simulation and then just complain and blame Autodesk for it? No, not at all. What are we going to do? We're going to scale our zebra and our scene as much as needed for this to work. Simple as that. So if you had a scene file with a camera and all that, you would just group it. Put everything inside a group, okay? Center your pivot, and go in here and scale it. Let's start with 0.1, for example, 10 times smaller. Okay, we got a little zebra. If you're scaling the camera, you're scaling everything else, everything will be fine. Not everything will look the same through the camera. And what do we know by now already? That whatever looks good through the camera is what we care. We care about the final image, nothing more. Yeah, we're selling frames. We're selling pictures. So make the picture look good. Doesn't matter what happens around it. And goddammit, you know this by now because you may have seen a lot of behind the scenes videos and you love to. I've seen that you post a lot on the group trailers and well, those making of and things like that. That's very cool. You should continue to do so. And there you will see that we only care, and directors only care what's seen through the camera. That just is very clear when you see those sets, for example. Okay, sets for a film set. You see that you only have just whatever the camera can see, but nothing beyond that. Isn't this stupid? Stupid to do that. Well, same thing happens for us. So if you scale everything properly, then everything will look correct through the camera. So there's no one will ever know. And I can tell you with property now. I can tell you honestly, I've done it. And no one ever found out. And that's not cheating. All we do is cheating in this thing. We cheat because that's effects, right? That's visual effects in general. It's a cheat. This doesn't exist. We just need to make it look cool. That's all. It's understandable that needs to happen. And like I said before, if you have a proper supervisor, someone with experience, someone who went through this before, you don't even have to do it yourself. He will ask to do it way before that. I've done it before. I've measured things before, and then just ask to fit everything in the proper scale. Otherwise, it will never work. So I don't want you to worry one bit about that. I heard many people over the years, care too much and think, well, but why am I going to scale the camera? Are you crazy? Not a problem, not at all. Okay, perfectly fine. So with that in mind, I scaled my zebra then 10 times smaller, right? I made it 10 times smaller than what it was before. So meaning I can grab my container and I can go in and just take a 0 out of each one of these sides, right? To make it 10 times smaller, right? Here it is, and here's my zebra. So I'm going to move my container down, and as you can see, once I come in, it looks exactly the same as what we had before. Same proportion, okay? The zebra occupies the same volume now inside the container as it was before. It's proportionate to each other. Great. So now we grab our calculator, excuse me. I have a bit of a cold, by the way, so that's why my voice may be a little funky. Plus, I'm recording this. It's not too late. It's 11:16 at night, but my girlfriend's already sleeping, so I need to, control my voice and all that. I prefer to work at night, as you may see. Keep an eye on the recordings. At the beginning, I was in a different country, and my apartment was different. So I had a space where I could record in the mornings. You will see a lot of AM recordings in here. Then I moved to Mexico and I recorded probably also during the day because the computer was right next to the bed, so I couldn't do this at night. And now I'm in Venezuela and I'm living in a hotel, and then I have a separate office in here, which is great. Close to my room, but not far enough for me to record at night, so I prefer to record at night. So you have seen probably lessons in 2, 3 in the morning. That's usually what I like to do. But my voice today is a little scratchy because I have a bit of a cold, so I apologize for that. So anyway, okay, so everything is 10 times smaller. I took off 1 0 of each one of these sides. I want to make sure now if my computer will be able to handle a 10-to-1 ratio. So let's go ahead and do the math again. So I have 100 on my biggest side, meaning that I need 1,000, right? 10-to-1, multiplied by 500, yes? 500 meaning that is 50, 10 times is 500, multiplied by 500 again. And now I have, okay, 3 6 zeros, 250 million voxels. It's not going to happen. Again, you don't have a computer that strong. I guarantee you that. Let's talk a little bit about that. How do I know that? How do I know that 250 million voxels is too much? Well, again, by experience. Okay? I can tell you, a computer with 64 gigs of RAM, okay, it's computers that I have used before. If you see the FX Power user, I speak in those terms back then because my computer back then, it had 64 gigs of RAM. Yeah. I could do with that computer probably 60 million voxels. And you will say, well, what does it have to do with RAM and voxel quantity? Good question. I will tell you a trick or something you should know. The speed of the simulation, okay, how fast the simulation will go from one frame to the next, is directly related to the processor of your computer. So if you have a fast processor, you might have a faster simulation because it's just data that is being calculated, right? Good. Now, the RAM is responsible for the number of voxels you may have. Okay, but that's memory that gets allocated, okay, and has to be held. So you need a lot more memory in order for your computer to be able to calculate those things, or at least have all the data in memory for the processor to calculate that thing. So the more RAM, the more voxels you can have. And then your video card is going to be responsible for drawing the fluid, for displaying it here, and drawing these voxels, right? So those are the three things. I tell you this why. Because this is why, and you will start understanding a little bit better where I come from and why I say the things that I say, is when someone tells me that because of the computer is old, they cannot take this course. And that's just bullshit. The only way you cannot take this course, and I could probably argue about that as well, is that if you don't have a computer, okay? But understanding these concepts and understanding what I'm doing so far, it could be done in an iPad, could be done on an iPhone, could be done on anything basic, old computer, okay? Just getting these things displayed and at least discuss these things, right? So you have to adapt your simulations and the scale of your scene, as you can start to see right now for this lesson, you have to adjust that according to the computer that you're using. And you may not go to millions and millions of voxels and beautiful, perfect simulation, but it doesn't matter. What matters to me, and trust me, it will matter to your future employer, is that you understand this, you know about this, and when you are in an interview, you need to explain these things, explain the ratio, talk about these things that we're talking right now. Trust me, my colleagues at lunch with me, if I talk about these things, they will be impressed. Not with me, but at least I'll make them think. I'll make them question a lot of the ways that they work. So you should bring these things up at your interviews. That way, if you show a playback of a simulation that is not, high detail, you have to explain. Well, I should mention, okay, that the computer that I'm using is a computer with this, this and that, and it has this amount of RAM. Because of that, I had to use a ratio of voxels against container size of 3-to-1, which I understand is not really high resolution, but at least I know that I have all the ingredients and I know all the knowledge. I have all the knowledge for me to make a proper, beautiful simulation. If you hire me and give me one of the computers that I know you have, for example, that's a very interesting phrase and a very interesting conversation on an interview. You're not going to take the computer from home to the studio. They're going to give you one. If it's a high, a big budget film on a high profile studio, trust me, they're going to have computers for you. But you already understand what to me is the most important thing, and Mohammed has pointed it out many times. What he finds as the big value of this course, okay, is the experiences and this intros and these conversations that we're having throughout, so far 20 lessons. This is enough to understand this. Then you can adapt yourself and be as big as Avatar at Weta, or as little, okay, as each one of you at home with your own machine by yourself. Doesn't matter, you can adapt, but you understand this, which is to me the most important thing. So, going back to this, 250 million voxels is impossible. Think of it in those terms. I don't want you to take those numbers so literal, okay? But 64 gigs of RAM. This morning I came up with a conclusion. Well, maybe think of it as 64 gigs of RAM, 64 million voxels. Think of it, baby, a million voxels for every RAM every meg of RAM that you have, or every gig that you have. Okay, so 1 million for every gig of RAM. It could be in your mind a good relationship, at least so you understand, okay, if this thing is going to work or not. What happens if it's too much? Well, the simulation may just close itself, stop calculating at some point, or it may just error out. So you have something that starts to move, and the density starts to jump all over the place inside the voxels, and or the container gets filled in one frame full of density. That's how you see a failure in the solver. Okay. So you need to anticipate. So in my case here, in this computer that I'm viewing this course, I have 32 gigs of RAM. So I know I shouldn't go over 30 million voxels. I shouldn't. Because there's a high probability that something's going to go wrong. If you have 8, which most computers come with that nowadays, well, man, stick to that. Stick to 6, 8 million voxels, probably 10. It's enough. It's a lot of voxels. You can do it. You can do it. Of course, don't do your simulations and have, Firefox open and music, and I hope you don't, but I hope you're not downloading something illegal somewhere, right? All those things are eating memory. Okay, don't have Photoshop and 3D Max and RealFlow open, because obviously your computer is being compromised already. So if you're going to do something like this, it's delicate, close everything. Everything. Okay? And just run it. But you can do it. You can do it. You can learn this thing, and you can understand it, and you can be as effective as anyone else in this course, regardless of what machine you're doing this. I promise you that. Okay. So 250 million voxels is not going to happen. Like I said before, I have a 32 gigs of RAM, so I shouldn't go anything over 30 million if I want to make sure that, I'll be fine. So that means, again, Mr. Zebra, you have to go down and get in size. Okay, so I'm going to go to half of that, 0.05. Okay, this is half the size, so I'm going to take these numbers and I'm going to cut them in half. 25, 25, and 50. Sorry, and 50. All right. Again, we're fine. I come closer and it looks exactly the same as before. But now I have half the voxels. So once again, calculator. And let's do it, 10 to 1. So first axis is 500. Multiply it by 250 by 250. And I have 31,250,000 voxels. Okay, I'm in range. For my computer, I'm in range. So at this size, with my current computer, I have a high probability of everything is going to be okay. Do that every single time you start a new shot. You're not going to take an hour like I'm doing right now, because I'm just explaining things slowly and I want to make sure that everything is clear. Something you're just going to calculate quickly. Sometimes, obviously, you don't need the calculator to do 25 times 25 times 25. You can do that, or have your calculator, make sure to understand this thing and have that data ready, and prepare and understand before you do your simulation. Otherwise, if you have to wait for things to fail and the computer to slow down to realize that your scene is too big, then you are wasting your time. and you deserve to be at the studio on the weekend. I'm sorry, but you do. Okay, so avoid this. That's what you're learning. That's what you're going to a course, so you're taking this time, that's what you made the investment to buy these things, these videos, okay? So, very, very important that you prepare yourself. Okay, a couple more things. Now, technically, okay, my computer can handle this, so I should be able to go in and put my base resolution. I haven't put it because I don't want to have, my computer to draw all those boxes for nothing, right? So I can do that. I can just go in and put my base resolution, which is 10 times more than this, and I'm going to be fine. But you never, 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 ever, ever should have a container with the display set to full like I have right now. It's ridiculous. This is just, you're putting a lot of burden into onto your video card. Okay, your video card is going to struggle, and then even if your computer can handle the simulation, your video card was not be able to display the container. So you should grab your container, okay, and keep it on the boundary box. You should keep it at bottom for a little bit while you learn. Okay, just so you can see what's happening. So I'm going to go in and put 500. Okay, Maya is not going to change yet, and there you go. Okay, so Maya is now drawing the bottom part of the entire container, which has, as you know, 31.2 million voxels. If I come close, you will see now that there are very little, okay, voxels, meaning that this simulation is going to be very detailed. This number here is not a magic number. That number on its own is nothing. All it's going to do is eat resources. If the rest of your container is not well set, not properly set, it doesn't mean anything. You can have a ratio of 30:1 and still look like crap. I'm not saying that's a magic number. I'm just saying that this is what it does. It's very important that you understand that it's a very delicate number, but you need to have a relationship, okay? But you also need to set your container properly. We're going to do that later. So for now, you shouldn't have, because you can see how my video card is struggling. Look, there's no density, there's no animation, no collisions, no particles, nothing. Just a container, that's it. And look how it suffers, because it's drawing all these things. So like I said, you should have that just to make sure, and then take your boundary draw and set it, for example, to something like bounding box. Okay, look, my computer is a little bit faster, but look, I still have a display that is a little bit faster than before, but still slow. That brings me to the next topic of conversation. Why is that happening? Why if I don't have anything happening, I don't even playing the simulation, why is my computer suffering if you already told me to get rid of the display of the bottom of the squares? There's nothing, it's just a big, the boundary box of the container. Why is it slow? Well, it's simple. Maya is holding in memory, okay? Well, Maya has that set up having 31.2 million voxels, so that information is there. It's ready to be used. It's like having one massive variable, right? So Maya needs to have that prepared for you to run it. So it's going to take resources. The only way you could avoid that if you were to grab this and hide it, that way, right, you get your computer back. Look, perfect. Okay, but if you want to have this visible, okay, then your computer is going to take a punishment for it. So what do I mean by this? Well, why am I telling you all this? It's because you shouldn't work at the render resolution. So you shouldn't do your simulations or your testing at a high resolution. This is a number, okay, this 500 of base resolution, okay? That's a number I'm going to be using once I'm done testing, once I've done my play blast, once I'm happy, and I'm going to go home for the night, okay, or I'm going to go to a movie with my girlfriend, okay, and I'm going to leave my render running. So I set it to 500, and I go and I let the computer work. I'm going to have plenty of time to practice those things in the next few lessons, so don't worry about it. What I'm trying to tell you here is that don't work during the day on a resolution of 500 because you're not going to get anything done. You're going to be waiting so long for anything. So that's ridiculous. I can probably guess what you're thinking. You might be, well, okay, great. If that's the case, so of course, why am I going to work with a ratio of 10 to 1? I'll do this. I work on a ratio of 1 to 1. And look, perfect. I get my computer back. I got my setup. I got my container on the right size. And I will tell you, no, you're wrong. Again, why you're wrong? Well, when you're running fluid simulations, okay, 10 to 1 ratio is clear that it's going to be used, for example, for rendering. Okay, we're happy. That's when we're getting close to a final version. But working on doing your testing on a 1 to 1 ratio is also going to be a problem for you. It's going to be fast, yes, but it's not going to be anywhere near the final look. And probably you start to guess, okay, why some people who doesn't know what they're doing with these solvers and with Maya will tell you, but Maya is crap, man, because I'm working with a fluid simulation, then I go ahead and put some resolution and it looks different. Well, of course it's going to look different. Didn't I just say that the base resolution is not a magic number? It's just not a beauty number. If it was, it would just call it something else. We'll call it a wonderful slider, or the make it pretty slider, or the please God save me slider. No, it's not that. It's base resolution. It's just a number, and it does something, but it's not gonna make your simulations beautiful just by increasing it. No. So what happened? Why is that? Why do people say that? Why they say, no, but I'm working in low res and I go high res and I just switched it from 50 to 500 and it looks completely different. Maya's a piece of shit. That doesn't happen in any other software. Well, you're completely wrong, my brother. Completely wrong. The reason is there's a lot of things being calculated on a fluid, and you will see them with me with time as we move from example to example, right? But there's certain values that are strictly related to the number of voxels, or they're calculated on a per voxel basis. For example, something called dissipation. Okay, dissipation is the ability, like the name tells you, right? Is the ability of the density to vanish. Okay, or to get weaker and weaker and dissipate or disappear. Okay, as time goes by, or as it moves from voxel to voxel. So the dissipation, for example, gets amplified once you have more voxels. It will happen to that. It will happen to the vorticity, or what's called the swirl. It will happen to the diffusion. It will happen to the buoyancy, and so on and so on. And that will happen for density. It will happen also for temperature, and it could happen to the fuel. There's too many variables. Too many variables that are connected to the number of voxels. So that's why a simulation set with a ratio of 1 to 1, once you go to 10 to 1, it's a different thing. You may have some resemblance, but it's not going to be near what you had before. So how do you fix this? It's not 1 to 1, it's not 10 to 1. Well, logic will tell you what? Try to work at least at half of what you're going to be rendering, right? So if I'm going to do my simulations here for testing, I'm going to be working with a ratio of 3, 4, 5 to 1, for example. I will try to go as far as I can, as close as I can to the final resolution without compromising my whole day just doing a simple thing. So that's another very important tip for you. So try to work, for example, at a ratio of, let's say, 3 to 1, so 150 to begin. And you can increase that number, but you can increase the ratio as you get further and further away on your simulation. For the first few things, you can start to 1 to 1 ratio quickly, just to see if the emitter is working, just to see if it's emitting off the right place, basic stuff. Then go to 2 or 3 to 1, just start to work on the look, and start working on the shading. Then try to go 4 to 1, and then 5 to 1 when you're kind of happy. If you're happy with whatever it looks at 5 to 1, then you can easily go to 7, 8, or 10 without looking and run your simulation. Again, like I said, don't worry about it. I understand this lesson. It has a lot of information, but you also have access to this and you can rewind it and watch it over and over again. It is mostly me talking, but it's a very, very important lesson. One of the most important lessons of the whole course. Because understanding fluids, understanding them well from the beginning, is going to set you apart from anyone else in your team. And this is something that you don't have to share with people. You can just keep it in your mind and do your calculation yourself and don't worry about it. But once your coworker is complaining and is crying because it doesn't work, then you can go to their desk and help. And say, you know what, let me just quickly multiply the resolution numbers. Yeah, you have too many voxels, brother. This is happening, that is happening. It's very, 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 very important for you. So in a situation like this will be a proper scale. If I wanted to bring the monk into the game, then I will probably, well, first of all, I have to show him. And where is he? I lost him. There he is. Just bring him in there. And give him more size. Let's put it next to him. Something like that, I guess. I don't know. That's the monk and his zebra ready to be involved in a fluid simulation. Another thing that is very important. Okay? A fluid simulation will only happen inside the container. Anything that is outside is not going to be included at all. So not only the emitter, but the geometry, nothing. Okay? Everything has to live inside your simulation. Your container, I'm sorry. For those of you who are taking the movie of the week program, okay, David, there's quite a few of you already. They're taking both courses. We already have, covered a few of these things. This lesson might be familiar to you, and you might have known from the first lesson or the Fury lesson when you have the tank. Okay, I did the simulation that way so you can understand that. Right? You need to have, if it's a big scene. Okay, on that lesson we have a tank shooting and you have the impact and the distance. I did it that way so you can understand that one simulation has to stay in here and the impact on a different simulation on a different container further away. Okay, don't have a massive container for space that you don't need. Remember, you have to be very economical with this. You have to be cheap. You have to think of voxels as they will cost you money from your pocket. Okay, that way you will keep it very, very sharp. The sharper you get it, the better it will be for you. Okay, remember that the more voxels you have, also the bigger the fluid cache is going to be. And another advice I can give you, now from the beginning, we're going to have to talk about that later anyway, but don't cache fluid containers if you don't need to. Because then you're going to start complaining and you will hear people say, well, but those simulations don't only look like shit, but they take a lot of voxels as well. And my hard drive is full of them. Okay? And how many versions do you have? Well, I have 5 versions. But why do you have 5 versions? It's too much. And why are you caching things that you're testing? That you can just render them directly, for example. Well, I thought you had to cache them all the time. No, you don't have to cache them all the time. Very important that. Very, very important stuff. So as we move along with other examples, I'm going to keep giving you tips. But for now, I think it's a proper amount of information for you to chew on. The next lesson, then we're going to jump onto the example that I told you about with Avatar. So you will see that even though I will consider my first and second lesson with fluids in this course, but it's the first time we're going to use it. And we're already doing something that is on a big film. And it's not only on Avatar, it's on every movie that has underwater environments, that has interaction. You can even simulate a breeze from a window on a curtain, for example, using this. So fluids not all the time have to be visible. In my opinion, they're more powerful when they're invisible as force fields. That to me is the most advanced force field you can use. If you love the volume axis, you're gonna love using fluids as forces. Trust me, a lot of fun. So a lot of cool stuff is coming your way. So be prepared, get your particles well, recorded and tattoo it in your mind, okay? We're gonna come back to particles because I know there are a lot of stuff that is still missing. I just thought that this being lesson 20 is a good round number to begin talking about this thing. But think about everything I said here, try to understand it, okay? And I will see you in the next lesson, which is coming very, very soon. I'm gonna finish this one and start with the next one right away. I just don't want to mix them because I want to each one of these lessons to be separate. This particular lesson, put a little mark on it and really, really get what I'm saying here, right? So I hope you enjoyed it. Thank you as always, and I'll see you in the next one. Bye bye.